Alright. So the circuit that we are going to build is represented by the logic diagram that is shown in figure A-3.1. This is experiment 7 part A, and we have digital channels now. So there's something new that we have not seen: digital input output. So far we have been looking at analog oscilloscopes and wave generators. We are going to be looking at digital channels now. The analog discovery gives us 16 digital I/O. So those are, you can take a look at that on the digital I/O at the analog discovery. If you look at all the connections on the right here, we have not been using them. The purple and the brown and the pink, all those connections starting from 0 through 7, 8 through 15, all those 16 pins, those are your digital I/O. So you can configure them to be inputs. So for example, switches or push buttons, or you can configure them to be lights that can turn on and off as outputs. Or you can leave them in high impedance, which means that they are not connected to anything. So you have those three options as far as input output for digital inputs and outputs is concerned. So we will be using those. We will still need to use power and ground, the red and the black wire, because we still need to provide the power and ground for our chips. So that's what we are going to try to do here. So let me walk you through the circuit board here and then compare that with the circuit diagram. Uh, so the one thing that I've noticed, which I really don't like, is students build the circuit looking at something like this, figure A-3.2, instead of looking at figure A-3.1. So personally, I would try to build things looking at a logic diagram or so for example, like a hand-drawn circuit, as opposed to building it on a proto board, taking a picture of it, and then building the board using that. Um, there could be a lot of confusion and there's no real learning there. So instead, what I'm going to do is I'm going to try to look at the circuit diagram here, the logic diagram here, and show you how I've made the connections on the proto board. So for this, I need chip 7402, 7410. Actually, I can make this bigger here. 7402, which is a 2-input NOR gate, followed by 7410, which is a 3-input NAND gate, followed by 7404, which is a inverter or a NOT gate. All those three chips are 14-pin ICs that you see on the proto board. So I've put them in the same sequence. So 7402, 7410, 7404. So those three are there. Something that is not shown in the logic diagram is the power and ground connections. So for all these 7400 series ICs, power or VCC or 5 volts is provided at pin number 14, and ground connection should be provided on pin number 7. So if I look at these chips, there is a notch on this side. So that means that this is pin 1, and I go counterclockwise 1 through 7, and on the other side I've got 8 all the way to 14. So I've connected 14, pin number 14 of each of those chips with that red wire to a power rail, and I've put a header pin here so that I can connect my red wire from analog discovery and turn on the power supply. Similarly, I've connected pin number 7 of each of them to ground using this black wire, 3 of them, and I've left a header over here so that I can connect a black wire from analog discovery to this point. Next, I jump into, say, pin the first chip. 7402. The inputs are provided on pin 2 and 3. The output is on pin number 1. So I've put 3 header pins on the 7402 chip, pin 1, pin 2, pin 3. So I can connect them to inputs and outputs, to digital channel 8 and digital channel 0, digital channel 1, as shown in the circuit diagram, which I'll do in a little bit. I have taken wires and connected pin number 2 of 7402 to pin number 1 of the next chip, which is 7410. I've done that because pin 2 in the circuit diagram, pin 2 is connected to pin 1 of the next chip. They are both the same digital channel 0. Similarly, I've connected pin 3 from 7402 to pin 2 of 7410 using another wire. Same reason, pin 2 of 7410 is the same as pin 3 of 7402, which is controlled by digital channel 1. The last thing is, that is also, another thing to note here is pin 2 of 7402 is the same as pin 1 of 7410 is the same as pin 1 of 7404. So I've taken that, mapped it to pin 1 of this chip, mapped it to pin 1 of this chip. So there are 2 wires there. And then I'm leaving a header pin on pin number 2 of 7404. I also need pin number 12 and pin number 13 of 7410. I have 2 header pins available for that over there. And then I have pin number 1 to monitor my output, which is over here. So that's how I've laid out the circuit, and I've made certain connections. And now I'm going to interface my analog discovery board with this proto board and access the digital channels. Now before I get into that, I hope you guys see that digital channel 0, 1 and 2 should be an input. So they should be connected to switches, push buttons, and digital channel 8, 9 and 10 should be configured as outputs. So for example, LEDs. Note that because these are inputs and these are outputs, that's why that choice is relevant. So let's start making some connections here and continue. So let's see, I have got a red wire going into um, that guy there. uh, for the next few minutes it is going to be a little bit um, not that nice. All right, I have a ground wire that I can connect to ground. So I've connected red and black so far. Next, let us focus on 7402. 7402, pin number 2 should be digital channel 0. Digital channel 0 from the analog discovery is the pink wire. Just to make sure I have the right pin, let's see. Alright, I'm going to essentially pull up so it looks like channel 0 is the pink wire. So let's start with the pink here. Pull out the pink and I can use this a wire to connect it on the board to uh, channel 0 was connected to pin 2. The next one is going to be 3 channel 1. So 3 is green. 2 was channel 0. I did that. Pin number 3 should be connected to channel 1. Channel 1 is the green wire. I'll take another wire here and connect it over here. And on the output I have should go to 3. The output is pin number 1. Pin number 1 is connected to channel 8. Channel 8 is let's see, pink stripe. So the pink stripe wire, I'm going to look at the pink stripe right here and make that connection to pin number 1. Alright, so I've connected uh, pin number 2, 3 and 1 of 7402 chip to the respective channels of analog discovery. Let's move on to 7410. So for 7410, I don't need to do anything about pin number 1 or 2 because those are already connected using these two wires. And but I still need to worry about 13 and 12. So for 12 and 13, say I start with 13. 13 is digital channel 2, which is the purple wire. Purple wire needs to connect to 13, which is right next to 14. And then channel 9 is green stripe. Green stripe is connected to pin number 12. Alright, the next thing that I need to do, so that completes my connections for 7410. And moving down to 7404, 1 is already connected to channel 0, and 2 needs to connect to digital channel 10. Digital channel 10 is purple stripe. So purple stripe comes out here. And I need to go to pin number 2. Alright, so that connects, that completes all the connections. I'm going to leave this in the view here, and I'm going to see how I can control these digital channels using waveforms. A quick note here, I have connected those inputs and outputs to those specific channels because that's what the figure says. I don't have to. I can use any one of the 16 digital channels and use them for these 6 input output purposes. I've just used 0, 1, 2 here and 8, 9, 10 here just because the circuit diagram says to do so. So note that. So let's see here. So no need, I still need supplies. So I'm going to go to supplies and turn them on. I don't need the negative supply. I just need the positive one. So I've turned on the master and the positive supply is set to 5 volts. So all the chips are right now powered up, so they are able to function as NOR gates and NAND gates and NOT gates. So next, let us go to static I/O. So static I/O is the option that we have to select the inputs and the outputs for all the 16 options. So I hope that you are able to see that on the waveform screen, which I advise you to make it the bigger screen now. Let's see, right now everything is set up right now as an output because they're all lights. But I don't want that. I want 0, 1 and 2 to be inputs. So I'm going to go to 0 and make that into, say, a switch and push pull switch. So that's a switch for 0, switch for 1, switch for 2. So I've got 0, 1, 2. Those are all switches and I can move them up and down. 8, 9, 10, I needed them to be outputs, and they are outputs over here. They're actually configured as LEDs, which I can leave them as LEDs. So let's see. So notice what happened over here. Channel 13 uh, became a 1. Right now it is not connected to anything. Channel 13 is what? Channel 13 is green stripe. Oh, okay. I might have connected it to the wrong input. Green stripe 9, channel 9 was the output of this guy. So the output of this guy looks like I have the wrong one here because they are so close in color. So what I'm going to do is, instead of this, I'm going to connect it to the other. There are very subtle variations in color, which is making this into a problem. Alright, now it makes sense. So I've connected, so 13 was also very close to a green color. Now I've connected to the right one. So now we are going to focus on 0, 1, 2, 8, 9, 10. Those are those are the 6 things we are going to bother about. So when all 3 inputs are 0, it looks like channel 10 is on, channel 9 is on, and channel 8 is off. So let's try to see, well, let's start simple. Let's start with the NOT gate. The NOT gate, the input is controlled by channel 0 and the output is shown on channel 10. So it is 0 and 10. So if I leave it at low, I would expect a high on channel 10, which it is. And if I go up here, it should turn off, which it is turning off. And then, so it's doing the NOT function as I go up and down. I hope you guys can see that. So that is essentially validating the NOT gate. Next, let us go to digital channel 8. So for digital channel 8, that the output is digital channel 8 for 7402. 7402 is a NOR gate. So it takes the OR between channel 0 and 1. So we are going to look at 0 and 1 versus 8. So 0, 1 and 8. So let's, alright, we can do that later. So when 0 and 0 for the inputs, 0 or 0 is 0, you flip that, it is a 1. So this should have been a 1, but it looks like it is not operational, channel 8, which means that I have a bad chip or I've not made the connections properly. So 0, 1, 0 and 1 are going into in 2 and 3, and the output is, oh, the output pin is wrong. the colors are so close to each other that instead of connecting it to pink stripe, I connected it to orange stripe, which is channel 1 negative. So now it's connected to the right channel. Uh, Give me a moment here. All right. Okay. Finally, I found channel 8. All right. So channel 8 is 1 now. Let's quickly do that 10 again for NOT gate. So NOT gate is going up and down. It flips. So that's good. Now let's validate the 7402 chip. So for 7402, 2 or 3, which is channel 0 or channel 1. So 0 and 1. 0, 0, OR is 0, NOR is 1. So that turns on. So that's good. Um, one of them is on. The output should be off. Like that is off. Both of them on is off. Even if the other guy's one is off. So the only time the LED is on is when both the inputs, channel 0 and channel 1, are low, which is the property of the NOR gate. So that validates my 7402. 7410 is a 3-input NAND gate. So for a 3-input NAND gate, all 3 inputs have to be a 1 in order for output to be a 0. So any other combination, the channel 9 is going to be on for every combination except for 111. So you can see channel 9 never turns off. It's always on. The only time channel 9 will turn off is when all 3 of them are 1. So that's the property of the 7410 chip. So all 3 of them are 1, only then channel 9 turns on. So this validates that my connections are all proper. I've connected the proper channel wires, and the thing that is very clear to me, and at this point you too, is that the colors are very very close to each other. So it's a little bit um, of an issue to connect the right wire to the right uh, digital channel. Okay, so another cool thing that we can do over here is if I go into settings, I believe, or maybe view, I can change the names on each channel. Let's say this is 8, digital channel 8 was the output of NOR. So 7402 out, and digital channel 9 was 7410 out, and digital channel 10 was 7404. Okay, I need to leave them on. Okay, so that's helpful as well. So as you're changing these, you can keep track of how the output is changing because you have named them. Similarly, you can name the other inputs. However, they are going across different chips, so that really doesn't make sense here. All right, so that completes part A-3.1. We have certain questions regarding this part. If I go down. So this is sort of what we did, and there are some questions that we are going. So for example, recording the truth tables, taking pictures. So I will do all of that at a later time. Um, I'm essentially going to be doing screenshots of channel 0, 1, 2, 8, 9, 10 and making them available for you I will not do this for all the 8 different possible combinations. I will pick a few and do that. Uh, so using those, you can answer the questions here. Although at this point, you probably can no because you have the background of OR, NOT gate, and the NAND gate. You probably can fill out the truth tables without even looking at this. In any case, I will give you the results on Piazza as I did for the previous experiment. All right, questions about part A dash, sorry, part A. So building this particular circuit. All right, it looks like there are no questions. Apparently, it was straightforward. So that's a good news. Let's keep moving. The time that we are looking at right now is about done, which means that I am a little bit behind because the flip-flop conversation, the experiment takes a bit long. So here is what I'm going to do. I'm going to stop here for today in terms of circuit building. We will pick up with the flip-flop experiment on Thursday. And on Thursday, we will also be talking about um, 555 timer, which is a pretty involved conversation. We'll talk about counters. We'll talk about uh, uh, you know uh, 555 timer. As you can see on the screen, this is a very interesting chip. It is essentially used to generate a clock signal. So the clock signal that we talked about earlier on today, having positive edges and negative edges, and a square signal that repeats at a particular frequency of a certain duty cycle, we can generate those kind of signals using a 555 timer. So we will be looking at all the details about this chip when we meet again on Thursday. But as far as experiment 7 and agenda for today is concerned, I guess this is it. I'm going to stop the recording here.